Good morning. We have been studying motion. We took a look at speed, velocity, and acceleration. Today, we're going to take a look at forces. And force and motion are two concepts that go hand in hand, they're interlocking. So, we want to talk first about what our unifying principle is today. It is that physical forces affect the movement of all matter on Earth and throughout the universe. Our big idea today is that forces change the motion of objects in predictable ways. All right, so that's the second thing. And then we're going to look at how force changes motion, at how force and mass determine acceleration, that forces act in pairs, and that forces transfer momentum. All right, so we want to talk first about the fact that forces change motion. Before we do that, I want to talk about two common misconceptions that we have about forces. I'm going to read you some information. It is that many students consider something a force only if there is an action associated with it. Passive forces, such as the force of a table resisting the push from a person, are not seen as force because the table does not move. And this is something we're going to talk about a little bit more. Passive forces are a very real thing. The second thing is that there's a common misconception that if there is no force on an object in motion, it will slow down. In fact, a force is needed to slow the object down. Friction usually slows down objects in motion. So it's usually friction. If you're kicking a ball on grass, it's friction between the ball and the grass. That's the force that's causing the ball to slow down. All right, so we're going to talk first about the fact that I'm going to try to set this up a little bit better so I don't forget anything. I've got notes and I've got a book, and try not to forget anything. All right, so the first thing is that a force is a push or a pull. So pushing and pulling are forces. Remember that we've talked about this earlier this year, that we measure forces in newtons, and the symbol for newtons is capital N. So a force in physics is defined as a push or a pull. I'm going to sneeze. Excuse me. Some forces require contact between objects, such as friction, and some act at a distance, such as gravity and electromagnetic forces. I want you to think about the fact also that forces can be seen by the naked eye. So if we're kicking a ball, we can see the force that's being applied to make the ball move. But again, some forces are unseen, like gravity and electromagnetic pull. So a net force is the total force that affects an object when multiple forces are combined. The net force depends on both the direction and the size of the individual forces. To show visually how to measure net force, we need to, 1, identify forces that we're combining, 2, put tail of second force to the tip of the first one so that we're measuring distance with forces because we're looking for net force. So we want to take a look at the size of the force and the direction of the force. And then you need to measure between the first two so that we understand how that the net. And I'm going to talk more about that, and you're going to get a worksheet probably next week on how we calculate net force. It's very, very simple. All of the numbers that we're going to use to help you understand this concept are going to be under 1,000. That's usually, it doesn't matter how big the numbers are with determining force, because it's the same principle. You would measure it all the same way. So we don't need large numbers to illustrate that force or that concept. Newton's first law relates to force and motion. So the key points of Newton's first law are that objects with no force acting on them have either constant or zero velocity. That's called inertia. And that's kind of a fancy way of saying is if I was sitting on the back of a pickup truck and there's no movement, I've got zero net force. I'm not going in any direction. I'm not going at any speed. I've got zero net force, and I am inert. I am standing still. And then the second thing is force is needed to start or change a motion. So that's key. An object that is in motion will stay in motion until another force acts upon it. An object that is at rest will stay at rest unless another force acts upon it. And that concept of inertia, and that's a word that you're going to hear all the time for the rest of your academic study of science, is inertia is the resistance of an object to a change in its motion. And it is directly proportional to the object's mass. All right, and again, this is a concept that we're going to go into more and more as we start talking. And we keep coming back to these concepts of mass, gravity, electromagnetism, force, motion. Those laws of Newton's, the four laws that Newton established, are so interlocking with everything we study. So we're going to keep coming back and back and back to that. We're also going to talk about the fact today that, so that was talking about force changing motion. And again, we've previously been looking at speed and velocity, and speed and velocity are something that affect force changing motion. But we also talked about acceleration. So the second principle that we're studying here, that force and mass determine acceleration. So Newton's second law relates to force, mass, and acceleration. The key points to Newton's second law are that the acceleration of an object is 1, directly proportional to the force that's acting on it. 2, it's inversely proportional to the mass of the object and in the same direction as the net force acting on the object. So if I kick a ball, it's going to move in the direction that I kick it. Okay, so Newton's second law is summed up by the equation force equals mass times acceleration. So F equals ma. Force equals mass times acceleration. We're going to have some sample problems that I'm going to show you today as part of a handout that I'm going to attach a little later today, and then there'll be another worksheet. It'll be your second math connection today. The other thing is that forces can change the direction of an object. So, and I want you to imagine this. You're playing kickball. You're kicking the ball to the other team. It's heading off in the direction towards them. They come running up and they kick the ball back. So the force of the second person kicking the ball changes the direction that it's going. So it's now coming back at you, whereas when you kicked it, it was going away from you. So force can change the direction of an object without changing its speed if the force that acts on it is at right angles to the motion. A force that continuously acts at right angles to an object's motion will pull the object in a circular direction. And that might be fun to try to do. Remember, it's at a 90-degree angle. The four 90-degree angles equal 360 degrees, which is a circle. All right. So any force that keeps an object moving in a circle at a constant speed is called centripetal force. The centripetal force needed to keep an object moving in a circle depends on the mass of the object, the speed of the object, and the radius of the circle. So if the radius of the circle is from the midpoint to the edge of the circle. So it's half the distance from the middle of the circle to the edge of the circle. So centripetal force, the formula for that is equal to mass times speed squared, because we're talking about velocity, divided by the radius of the circle. And this is a concept actually that you're going to we're not going to do any math problems or anything on centripetal force, but that is a concept that you are going to come back to as you go up through middle school and high school, and you get to studying physics in high school. So that's a pretty, again, a pretty interesting force, but again, it relates to circles, all right? Centripetal force relates to circles. The other concept that we want to talk about today is that forces act in pairs. So we've had Newton's first and second laws. All right, we're going to talk right now about Newton's third laws. Actually, I think I said Newton's four laws earlier. That was I misspoke. Newton's 3 laws that we're going to study today. So Newton's third law, which is my favorite, because you can have so much fun with it, is that Newton's third law relates to action and reaction forces. So the key points to Newton's third law are that when two objects interact, the force of object A on object B will equal the force of object B on object A. So what we say to in terms of like current sort of parlance is that for every action, there's an equal and opposite reaction. So in action and reaction pairs, either force can be considered the action or the reaction pair or reaction. The two forces will occur simultaneously. And here's an example. When you push down on a table, the force from the table's resistance increases instantly to match your force. Action and reaction forces occur when two objects interact, and that's not just through contact forces. So the pull of the earth on a falling baseball is exactly that of the baseball on the earth. The earth is more massive, however, and the earth's acceleration from the pull is nearly nothing. The acceleration of the baseball then becomes quite noticeable. And this again is, we've talked about this a couple of times, but not in these specific terms. We're not going to go in depth in terms of this too much as part of working up to our study on energy, work and power, but we need to talk about it a little bit so that you understand how forces act on an object. So the other thing about Newton's third law is that we can describe and predict motion with that. So Newton's laws work together to explain changes in the motion of the object, such as a squid moving forward when squirting water backward, or a bird flying higher or changing direction. Newton's laws are also useful in calculating how objects move under the conditions found in everyday life. Scientists such as Albert Einstein have added to their understanding of Newton's law of motion. And remember, we talked about this quite a lot with E equals mc squared. When we were studying astronomy, Albert Einstein knew that it wasn't just enough. Newton's third law wasn't enough to fully explain how everything works. It helped in terms of how everything works on Earth, but not in space. And we talked about this a lot. And so it was through exploring this idea and trying to make it fit what happens in space that Newton came up with some of his laws, one of which was that mass bends time. So, and we had that experiment of the guy that set something heavy in the middle of a stretchy cloth, and how objects move around it but eventually pull toward it because of the pull of gravity. There's a lot of big concepts today. I've got some good videos for you to watch to help explain this. It's a big concept. We just need to grasp it a little bit in terms of understanding about how force and motion interact and relate to one another, and about how force affects how something moves, so how much energy there is created and stuff. So we are going to talk a little bit next week. Remember, tomorrow you have a quiz. There will be a short lesson with the quiz, and what we're going to talk about is that forces transfer momentum. We haven't talked about this concept of momentum, and it is in and of itself, momentum is a huge concept. We're only going to touch on it a little bit so that you understand that force affects momentum. And momentum is the ability of an object to, take energy as it moves forward. So because it's an energy-related concept, we're going to talk about that. So I hope you're having a good week so far. I'm really, really pleased with the fact that everybody seems to have caught up. I tried to figure out yesterday how to send progress reports by mail through Schoolmaster, and it didn't work. So I'm going to send them out probably. It's going to take a while because I'm going to have to send them one at a time. So I'll take care of that probably this weekend in terms of getting your progress reports sent to your parents by email so that you know where you're at. Get outside. Tomorrow's going to be our first triple digit day. It's going to be so hot. And then next week we're supposed to be in the triple digits. For those of you who have pools, that's probably cool. But for those of us who don't, that's not so good. The quiz tomorrow is on these concepts we've been studying. I would say review the YouTube videos mostly for the quizzes. It's not going to be a big quiz, and there will also be a short lesson tomorrow. All right, so don't forget Zoom office hours at 10 o'clock today. I hope to have you turn in. Please bring questions. Bring questions, all right? And I'll see you then. Bye.